Good morning and a warm welcome to the first session of our Digital V-Days. We had just some little issues, but no problem. That's typical for this week of a lot of different presentations. 32 presentations we will broadcast this week. And I'm very happy to start with the first session this morning. We are in the topic of single pair Ethernet. And I'm happy to have Simon Mark with me today. And before we start into the presentation, into the session, I will just point out some little things for you in this session. So you will be muted. This means that you cannot ask us your questions within your microphone, but nevertheless, you have the opportunity to ask us all your questions in the chat. So then after the session, we will go into your questions, and then we will just have a live Q&A there. And if we can't answer all your questions within this time, we will answer them later on via email. So then also you will get the handout, the PDF file from us, and also the recording we will link later this week, and you will get all the links there. So then I'm happy to give over to Simon and enjoy our webinar.
Hello and good morning to this session 10 megabit single pair Ethernet over short range. And I'm very happy that you are joining this session, and I want to go with you through several new topics. To me, I'm Simon Mark. I'm working since 2017 in the company Würth Elektronik, and here in this company I'm responsible for simulation, measurements, and especially for single pair Ethernet. Today we want to go over 4 different topics, starting from Ethernet to SPA, then looking on the technical data, then from automotive to industrial, and at the end looking on 10BASE-T1S in detail to know what we have to define or to design during the process. Little bit to this history. I think everyone knows multi-pair Ethernet. In the office, everywhere you need, you use and you need Ethernet, and you have the 2-pair Ethernet cable here, 100BASE-TX, and also 4 pairs like 1000BASE-T. This is the standard Ethernet cable starting from, I think, Cat 5 to Cat 7. You have everywhere in your environment. In the history, or in years ago, the automotive industry started to use also Ethernet, but they found out that this is too heavy, too big, not so cheap. And so they they used a different approach. They used 1 pair for 100BASE-T1 and also 1 pair for 1000BASE-T1. They reduced the size, the cost, all of them to a simple twisted pair cable with a small connector. So that we have now only a twisted pair cable here on the picture with a shield and with a beautiful shielding. But in real automotive world, you have only twisted pair cables for 100BASE-T1. About the history, the standardization for 100BASE-T1 started, or ended, better to say, ended in 2015. And then 2016 was the standardization of 1000BASE-T1, also for automotive. And then years later, 2019, was the standardization for 10BASE-T1L, 10 megabit over a long range, here in this case 1000 meter, 1 kilometer. And also in the same standard it is mentioned for a shorter range, 15 meter or 25 meter, for especially the automotive industry. And this would be today our topic, to look on 10BASE-T1S. This was not the last standardization, but also 2020 was for multi-gigabit single pair Ethernet, the standardization finished. Then 2023, last year, was the finalization for more than 10 gigabit single pair Ethernet, and next year, hopefully, should be the standardization for a multi-drop single pair Ethernet for 10 megabit finished. And in this case, we can reach up to 50 meters, lots of multi-drops, and also power delivery. This is the idea for 10BASE-T1M. And end of 25 is also the idea to finish the 100BASE-T1 over longer range, like 500 meters or in this range, hopefully a little bit more. A short look on the wiring length. So starting from 10BASE-T1L, we can use 1 kilometer. At the end of the graph, or on the top, we have 10 gigabits, and we are only up to 15 meters, especially for the automotive industry. For our case, we have 25 and 15 meters for 10BASE-T1S. And for the bandwidth, we have very similar bandwidth to 10BASE-T1L because it's the same speed and there is no big difference. Now we go to the MDI, the media dependent interface. For automotive, for 10BASE, 100BASE and 1000BASE-T1, you have the same circuit or recommended circuit. Starting from the left side, from the PHY, you have the COM mode choke, some capacitors and a COM mode termination on, and the automotive connector. For the speed for 100 megabit in industrial area, for 100BASE-TX, you need 2 pairs. On the left side, PHY, RG45 connector, the big one, and then you need these 2 pairs. Lots of components, it looks bigger, complicated. And for single pair, we thought about only using 1 pair. So the same circuit, but only for 1 pair to establish this isolation and use the same components, hopefully. But this was not only the only part to look for. For the automotive industry, you need some requirements like the isolation, COM mode attenuation, return loss, mode conversion should be cheap and small. And you can establish it through different points. Like here, we have these 2 capacitors. We can establish the isolation of 60 volts. The COM mode choke and the COM mode termination establish the COM mode attenuation. Then also the COM mode choke and all the design around should be good, should be matched good, so that we have a good return loss, and also the mode conversion through the COM mode termination and the COM mode choke can be established. And all these components are small and cheaper than a big LAN transformer with all the circuits around or components in the circuit around. But in industrial area, you have a little bit different requirements. It is similar, but you need, for example, at the beginning an isolation of 1500 volts. You can establish it through capacitors only, but it is expensive, they are big, so the easiest way is to do this over magnetics. In our case, we have here the magnetics, or one transformer, the T1, and the capacitor C2 to establish also an isolation between the wire and the ground of the whole circuit behind, like the IC and all the intelligence behind it. Also the DC isolation should be there. Therefore we use C3 and C4 as a DC isolator. Little bit more than later, how to find the right values. Then also the COM mode attenuation. The transformer by himself is a very good COM mode attenuator in the lower frequencies. For the higher one, you need also the COM mode choke. Return loss, the whole circuit should be good, should be good matched. Also the mode conversion through the COM mode choke and also the ESD protection on the PHY side. Some details about 10BASE-T1S and L. What is the difference and what is the similarity? For 10BASE-T1L, the long range, we have only, or to start it here, we have a data transmission in full duplex. We have only a point-to-point connection and 2 nodes, because it's point-to-point, and a length up to 1 kilometer. So there is no multi-drop or lots of nodes on a bus line. It's only point-to-point. For 10BASE-T1S, it is a little bit different. It is like a bus structure, or you can use it also point-to-point. The data transmission for a bus structure is only half duplex. A little bit later, the next sheet, I explain how it works in a very rough way. And the system is a bus, not point-to-point. We can establish from 8 to 40 nodes, so you can use lots of nodes on the line, and the length can be up to 25 meters. Some IC manufacturers talked about longer ranges, but according to the standard, it is up to 25 meters. You can use it also point-to-point and then switch to full duplex or use only in half duplex. Then you have only 2 nodes, but then the length can be only 15 meters for point-to-point. So you see the difference. If you want to use it point-to-point, then the best way is to use 10BASE-T1L, because you can extend it up to 1000 meters. If you use this standard with the S for the short range, you can look for a bus structure, use lots of nodes, but then you are only can use 25 meters. How it works? It's a very short description. I will not say that I'm an expert in the PHY structure, but this is only some small summary. So every node has a specific number. Then every node on the line has a specific time to send that data. So this is not like in standard Ethernet, everyone is sending at every time. And in the time a node is sending data, all other nodes are high impedant on the or at the PHY. So they are listening on the line. They are not disturbing the communication. So we have here on the right side a bus line, and every node has a number like node 0, 1, 2, 3, 4. And it starts with a beacon signal, and after the beacon signal there is a short silence, and the first node, like node 0, has now the opportunity to send data. In our case, node 0 sends data. Then after the sending, there is a short silence of 16-bit. And after the short silence, node 0 can send data. Node 0 can also say, I don't want to send data, but in this case, it's also sending data. And after node 1 is sending data, there is a small error. It is node 1. Not node 3. But here node 1 is sending data, and after the sending, node 2 has the opportunity to send data, but node 2 don't send data, so there is a silence of 32 bits. And also for node 3 and 4. And every time one node is sending data, all other nodes are listening. They are not sending data. So this is the advantage of using this single pair on a bus line. But you have only half duplex. You have not this advantage of other bus systems or of other Ethernet that you have full duplex transmission. The circuit design. If you want to design now the circuit, the MDI, what you can do. This is the smallest circuit you can design. You can use here the transformer, like I explained before, as an isolation, the galvanic isolation of 1500 volts. Then you have also the capacitors for the DC isolation, some common mode termination, and the diode. This is the smallest circuit you can use for 10BASE-T1S and L. For the T1, we are using a 350 microhenry transformer in a small size of 1812, so it's 4.5 millimeters times 3.2 millimeters in this size. It's very small. And the two capacitors for the DC block are 100 nanofarad capacitors. You can also go higher to 470 nanofarad. This is then more for 10 base T1L for the longer distances. For the shorter, you can use smaller ones. Why? I explain it later. For the resistor, we looked for the best value, and we find out through simulation and measurement that the best value is really 75 ohms. You can also use 100 ohms, but for the mode conversion it was on the best value, but you can improve it by using different values. For the capacitor to ground, we have a 1 nanofarad capacitor, also with an isolation of 1500 volts minimum, to establish also the isolation between connector, so between this cabling and the circuit ground on the side. For C1, so this capacitor on the phi side, we have also 100 nanofarad, but you can use a very small in size, like also not 100 volts isolation. You can go down to 50 volts or 16 volts because you are not using high voltages on the phi side. And of course the TVS diode, here in this case, this is one for higher transmission signals. You can use it also. It's very small, so you don't get problems with the size. But this is also some rough idea. If you are developing your single pair Ethernet design, then if you have questions, you can go in contact to us and ask. We will support you to find the right solution for you. Maybe there is some better part for your case, and we will support you. Yeah, after the circuit design, we can simulate it and look on the values. The simulation are based on real measurements, so we are using real measured values from the transformer, from the comb mode choke, and therefore they are reliable and are working. And yeah, we have years of experience to say, yeah, our measurements are validated and you can trust, or we are trusting them. And after several measurements and simulations, we build up, of course, our circuit for example, 10 base T1L or higher data rates. And this was every time a very good match of measurement and simulation. Yeah, here you can see on the graph the green line. This is the limit for 10 base T1L, and the yellow for T1S. And I included both of the limits for the return loss, and you can see on the black line we are far below the line, so we have enough space or margin. And also for the mode conversion, here is the T1S and the green one T1L, and with our circuit we have lots of margin and are below the limits, so we are according the limits. Maybe someone wants to design a even better circuit to achieve open alliance limits. Only the limits, not that we use these components in the automotive industry, but to be in a better, have better attenuation, better return loss. You can use, for example, also the comb mode choke and the comb mode termination circuit, and also only this 100 volts, 100 nanofarads, C3 and C4. This is also possible. Then you don't have this 1.5 kilovolts isolation between these connectors and the phi. Here you can use our comb mode choke like this one. This is also in the same size like our transformer in 1812, and the values for the capacitors are the same, 100 nanofarad. The termination circuit is defined through the open align standard with 1.5 kilo ohms with a very small tolerance of 1%, and also these values are defined. And here we get for the return loss a very good return loss, even better than before. Also for the mode conversion, don't be focus on this graph, not on this text. This is wrong. It is mode conversion, the SCD11. We are also below the limits. For the insertion loss, we are better than the recommended ones or the limits. And also for the common mode attenuation, we are below the limits. So in this case, you can use these values or these components for establish a very close match to the open alliance limits, but not to this other standards like to use this in automotive. An additional point is the droop. For the 10BASE-T1L, there is mentioned that the PHY in test mode will send several signals, and the droop, if you measure it, should be below 10%. This is the explanation for the droop for 10BASE-T1L, and for 10BASE-T1S, it should be maximum 30%. So in 10BASE-T1L, you are measuring the initial value, the zero crossing, and after the zero crossing at 133 nanoseconds, and after 800 nanoseconds after the zero crossing, you measure the values, and if the droop is then below 10%, this is a good circuit, so it is according to standard. For 10BASE-T1S, it's a little bit different. It should be below 30%, but you are looking after the initial peak. So after the zero crossing, there should be a small jump of the signal, and this is the initial peak. And after this value, 800 nanoseconds after this initial peak, you measure again. And this both you take in relation, and if it is below 30%, you are good with your circuit. In our circuit, we are looking mostly on the C3 and C4 to work on the droop, because the common mode choke is in our case finite. In this way we say, okay, we will not change the common mode choke, but we can play with the capacitance. And here, if we use a 100 nanofarad capacitor, we have a droop of 13%. If we go higher to 220, we have 9.4, and with 470 nanofarad, we are at 7.8% of droop. So to explain it, for 10BASE-T1L, you need a capacitor of 470 nanofarad to be under 10%. Maybe you think about, okay, you can use 220 nanofarad, but this is not good. I will explain it in the next slides. For 10BASE-T1S, you can use starting from 100 nanofarad and up to 470 nanofarad. And it will work because you have a droop of 30%, which is allowed, and here we are maximum at 13%. The placing of the capacitors, you can use it on the line to put two capacitors on the line, or you can go and put one in the center tap termination. This is only possible for our transformer because here's on the connector side and split the termination, so you can establish a center termination split and solder a capacitor between, and then you have this isolation capacitor on the line. But the problem can appear here. Every capacitor has some saturation. After some voltage is on the capacitor, he saturated according to the line. We have in most cases X7R material for the capacitors, which are used for these SMD capacitors, MLCCs. And here we are on the line where we can look for the saturation. For example, for 15 volts, we have a loss of 10% of capacitance. At 20 volts, near or close to 20%. And so you can look for your capacitor and then find the point when it's saturated. Also, the temperature affects the capacitance. On room temperature, you have this 100% or 0% difference. In colder area, you lose a little bit. If it is higher, you lose again a little bit of capacitance. And also the aging. After you power your circuit and several hours later or months later, you lose a little bit of capacitance. In the beginning, it is like 1% in 10 hours. But if you look 100 hours or 1000 hours, it's more than 2%. And in most time, you implement a circuit or a device, and then it runs for days or weeks. And this should be also taken into account. I made a small calculation. It's a very rough calculation between 470 nanofarad and 100 nanofarad capacitors with the same voltage and the same type. After the DC saturation, so if you implement this 10-base-T1L for a power over data line circuit, for the power over data line, we have also different webinars. You can look on it. There is a little bit more explanation about the power over data line circuit, how you define it and what to take in account. But here in this case, if you have, for example, 24 volts per capacitor, you lose for the 470 nanofarad capacitor around 38% of capacitance. For the 100 nanofarad, only 5%. Now you have only for the 470 nanofarad, 290 nanofarad left. For the 100 nanofarad, you have only 5% of loss. Then you take in account the environment change, the temperature in the environment, and it change. So you can lose also additional several percent. And after the third one, the aging, you lose again 2%. You have only 280 nanofarad from 470. From the 100 nanofarad, you lose only 11%. So it is still okay, because now if you calculate and look on the droop, we have for the 470 nanofarad 9.34%. And for the 100 nanofarad, we have 70%. So in this case, you can use only this capacitor for 10-base-T1S because you are still in the range. But for the 470, you can use it still for the 10-base-T1L, but a smaller capacitor would be saturated, changed in temperature, and after aging, lower than this 280 nanofarad, and then we are losing this margin and cannot use it for 10-base-T1L according to the standard. You can check the loss or the saturation or the capacitance change on our RedExpert tool. Here you can see the capacitor you can choose, and then you see the curve where you can compare, for example, the 470 and the 100 nanofarad capacitor. Then you see the change in percent over the voltage, and on the right side, the change in percent over the temperature. One additional point for 10-base-T1S is the termination on the bus line. So according to the standard and also in the PHY chip datasheet, it is mentioned that you have two options to match your bus line. One option is on the bus line, so you have your bus line on the end, on both ends, you implement 100 ohms and put on the bus line every circuit or every device, and then you have an established terminated bus line. The other option would be to use it direct in the circuit or on the MDI. So you have here, on this case, an open bus line, but on the end, on both sides, you have a different circuit. Like here you have only capacitors before the connector, and here you have even a small termination circuit of 100 ohms. Yeah, this is the possibility to use your termination inside of the circuit, not on the bus line. My last slide is about the PHYs. A small summary from this side is on the left side is the 10BASE-T1L. So we have from analog devices several ICs for the 10BASE-T1L, also from Texas Instrument, and for the 10BASE-T1S from onsemi and Microchip. And they are more deeply explained about how it is working, the software characteristics, which are not the topic of today. But yeah, if you have questions about how to define your circuit, what to establish there, what you have to consider, you can come to us, to the colleagues. We will look on it and find a right solution for you. Now you have the time to ask us. And yeah, I'm here waiting for your questions. Thank you for listening.
And yeah, this was the presentation of our first session with the topic of single pair Ethernet. So Simon, thank you very much. And now we want to start into the Q&A session. So yeah, we will have a look there. Just an information, I will quickly share also the handout with you today. So we prepared that already. So one moment, I think you should see it now. So yeah, you can download it. And also, of course, we will share all the links with you after the session in the next few days. So I see Simon is now also with us. Of course, we pre-recorded the session last week because we wanted to ensure that the quality is very good. And now we have also live Simon with us. And we are starting right into the first question. So Simon, first question was here. Are you sure about your DC bias values you're presenting? Look way too optimistic to me, especially for 100 nanofarad. That is usually the lowest quality and cheapest part that can be produced is the DC bias, easily even something like 50%. So yeah, Simon, can you answer this question, please?
Okay, good morning from my side. I hope you can hear me. Yeah. Okay, so the internet connection is good. And yeah, thank you for the questions also from my side, and thank you that you joined the session. And for this question, I think this is a question for the product management in our company, but I can say with, how to say, I'm trusting the product manager because they used real measurements in the laboratory. There is not a simulation or calculation behind, but this was a real measurement of the capacitors during all these steps. And you can find the graphs in our Red Expert. And if you want to try it by yourself, you can try also the capacitor measurements. But yes, to say this is the values we are providing, and this is the minimum value the capacitor has as an DC bias.
Okay, Simon, thank you very much. Then let's go on with the next question. Is it possible to use power over data line for 10BASE T1s?
Yeah, so this is a good question, and I looked in the last weeks also around this, and I searched different applications, but at the time I don't find a real application which is provided on the market. Also the PoDL chips from analog devices are only mentioning or have reference designs for 10BASE-T1L, but I know customers are working on 10BASE-T1S and the PoDL topics, but at the time what I assume is the problem with this lots of nodes and to power all of them, and so there is not a finite solution, but I hope that will be in future one, because in the standard, in the IEEE standard, the PoDL topic is mentioned for both for 10BASE-T1S and L. There is no separation only for L, what I found, but yeah, you can correct me if this is wrong. Yeah.
Okay, so thank you very much. Yeah, then let's dive into the next question so we can use our time. Yeah, so the next question is, do you have proposal for combi layout for 10BASE-T1s and 100BASE-T1s?
That's a good question. And as you looked on one of the sheets, you can open the PDF you get from Markus, and you find inside on the page, let's look where I mentioned it directly. On page 27, I mentioned that there is for 3 different capacitor values from 100 nanofarad, the droop of 13%, and up to 470 nanofarad, the droop of 7.8%. And I said that here you can use 470 for 10BASE-T1S and also 470 nanofarad for 10BASE-T1L. And this was the assumption that if you use 470 nanofarad, the same transformer and the same circuit around, it will be possible to use it for both applications, so for 10BASE-T1S and L. But what you also have to do is also the matching or the termination on both ends if you want to implement a T1S circuit, but this is an additional part. So if you look then at home on your screen, it is on the presentation, it's the page 27 where I mentioned it.
So sorry, we just showed the page 23, so then maybe we can quickly hop to page 27. So yeah, just that you can have a quick look again. So then, but maybe let's go on with the next question. Simon, we still have a few minutes left. So I just have to finish it here. Perfect. So do you know if there are also multi-port switches and power over data line controllers available for 10BASE-T1L?
Multi-port switches and PoDL controllers. PoDL controllers, yeah, from analog devices, there is a PSE controller with 5 ports, so you can use it as for a 5-port switch. And for 10BASE-T1L, for not PoDLing, also only for 2 ports. I know also from analog devices they have a 2-port switch, but more ports than 5, I have no information. So on the last slide, on 37, where I mentioned, oh no, this is the PHY chips. So I think I don't mention the PoDL controller. But if you look on the analog devices website, then you find PoDL controllers for 10BASE-T1L, and there is the PSE controller with 5 ports. Yeah, for a 5-port switch.
Okay, Simon, thank you very much for your question. Then I think we will come to the next and last question. So this is in automotive specs, at least 15K hours of, okay, this is a really special question. I think we will answer that later on via email. So then next question, in the schematics, there are different grounds, left and right, for the transformer. Where is the right one connected to?
This is a very good question, because it is depending on your application and where you are using it. In industrial area, the best point would be to connect all the grounds on one ground layer, but this is not the best way. And also, if you have a long cable and long distance between two devices, then you have lots of issues with the potential, and therefore the recommendation is only to have the ground on one side, and on the other board there is no ground connection. But on the board there are also lots of ideas where you can connect it and what is the best solution, and therefore I will send, or I recommend, the app note about our gigabit Ethernet, or Power over Ethernet gigabit board. We have several app notes and reference designs, and go to this one, look on it, and there you get lots of information about the ground of the transformer on the secondary and primary side. And this is mentioned, documented, and also the data, the Gerber data or ODB++ data are available. You can use this in your own board design.
Okay, so then, Simon, thank you very much for your time today, for your presentation and all the answers for the questions today. And of course, we couldn't answer all your questions, but the open questions, we will answer them later on via email. And if you still have some questions left, just email us at digital-v-days@we-online.com. So thank you very much for your attention. I hope you will join maybe another session also of our Digital V Days. And yeah, have a good day.
Thank you also from my side, and have a good day. Bye.